Okay, yeah, I'm gonna start it. Okay, thank you for introduction. My name is Hamram Lee, and I'm from International University. And today I'm gonna talk about, my main research field is atomic layer deposition, which is the thin film deposition technique based on the surface chemical reaction. And then my main application is semiconductor fabrication. Okay, yeah. I come from the International University, and also I am an executive editor of chemistry material of ACS publication. And then I have a very strong collaboration with a lot of the semiconductor industry. Also, I'm now working as a consulting professor in the SK Hynix, which is the top DRAM fabrication company. Okay, let's start for semiconductor because this is the workshop for chemistry or chemical engineering and biotechnology. So I'm not very familiar with the physics, but interestingly, to fabricate it, to realize semiconductor device, we have to fully understand chemical reaction. For example, this is the chemical reaction taking place in the PR for the deep UV. This is very key chemistry. And then this is the another the example of why the chemistry is very important because we deposit a lot of the material and we have to understand the chemical reaction because we use the CVD, chemical vapor deposition, or atomic layer deposition, ALD. So, start why we studied about semiconductor. I really like these three category of the Homo sapiens capacity, limitation of the Homo sapiens capacity. We are Homo sapiens, right? So we have hands, and we move on to the sun, and we move on to the bronze, and we move on to the android, right? So we cannot use our hands to fabricate this thing. We need to have a tool. So we have to use the tool. And then the second thing, we have a legs. But what is the maximum, the distance you can work? Maybe 40 kilometer per day. That is a quite the maximum distance for the common Homo sapiens. But if you use the horse, if you use the car, and we are now using shuttle. So it can limit our beyond our capacity. And then the second thing, which is the most important thing, is we have a brain, and we have a lot of tool, computer, and we are now using AI. So using the AI, it's a very meaningful change in Homo sapiens history. Our computing power is increased a lot, right? So that is the really, really important thing because computing power can affect a lot of the other field. Like computing power is essential to fabricate the space shuttle. Also very important for the fabrication of the Android and operation of the Android. So we have to use AI for the Android, right? So to realize this AI and computing power with the GPU at this moment, like maybe TPU. So to realize GPU, so this is the structure of the common architecture of the common GPU. It composed of the processor unit and then the memory unit. Everything is composed of semiconductor. So I don't have any additional words why we keep focus on the semiconductor. So this is very great message for our future of the Homo sapiens. And then because of that, this is the stock market chart of the SK Hynix. It's increased a lot. I think that yesterday stock price is the 1,600,000 the stock. So why ALD is very important for the semiconductor? So device, we have to want to have the faster device, higher capacity semiconductor. So to realize that we have to change all device from the two-dimensional to three-dimensional. So this is the key solution. But unfortunately, this is the some quick movie to show how fabricated semiconductors. This is the exact same process how we can fabricate the two-dimensional semiconductor process. We deposit some material, make a pattern, and remove unwanted area. Repeat, and repeat them. This is the how we can develop our semiconductor fabrication process in the last 70 years, right? So think about that. If you want to make this the full three-dimensional structure, how you can make it? For example, so if you use just a thin film deposition, which is the very suitable for the two-dimensional fabrication, so they cannot make it. So if you want to make this the three-dimensional structure, you have to use very conformal deposition around the three-dimensional structure. So ALD can make so ALD is the vacuum thin film deposition in the vacuum environment, and then it is continuously exposed to the precursor and then reactant. Chemical reaction is taking place on the surface. And then this is the example of aluminum oxide deposition. And then we use the TMA, three-methyl aluminum, and then also we use water to fabricate aluminum oxide. This is the full chemical reaction. So to understand the ALD, you definitely should be very chemistry person or chemical engineer. So this is a very important thing. Because of that, the ALD is used for the different type of the technology in the semiconductor fabrication. ALD can be used for the patterning process, etching process, dry photoresist process. If you are interested, you can read my editorial and review to explain how the semiconductor industry can expand their technology. Okay, so this is the most important message. Why I'm talking about the AI and semiconductor. Think about that. NVIDIA, SX, Samsung, and TSMC, they are semiconductor fabrication companies. So thanks to their efforts, they can fabricate great devices. We can realize a lot of the AI service. We can use the ChatGPT, Gemini, like a DeepSeek over years, and then Claude. So it makes it possible. But think about that. Semiconductor fabrication process is the most complicated process that human made so far. It necessary 600 or at least 1,000 every single step. So it is a very much complicated. It is a very much tricky to find the performance. But if you imagine, if you use this AI technology to make invention or revolution, innovation in fabrication, we can reinvent so we can make a great semiconductor device, and the semiconductor device can allow us to develop the better AI technology again and again. This is a really positive proof. So because of that, I am very much interested in how we can apply the AI technology to improve our ALD or semiconductor fabrication technology. This is a screenshot of my research group website. And then I really like these words, bridging experimental computation. I am experimentalist. I have been experimenting in the last almost 5 years. But I am very much computing. So look at this. I have an 8 ALD chamber and a lot of experimental. But today I have the AI, which is a very much computational skill. So think about that. I think you heard about the virtual AI and the physical AI. I think the experimental is the physical AI. So we had our physical experience. And then virtual AI is the same to theorist and then computationalist. But because of the development of a lot of the AI, experimentalists can easily use this computational thing. So we don't need to have like, is there any theorist here? So we don't need to have very strong collaboration with the theorists in many cases, right? So my research group is working on the density function theory, but like few years ago, so we need to have the strong collaboration with the theorists in the density function theory, but we can calculate it by ourselves because of this machine learning or deep learning process. So this is a really great sign to experimentally. I am experimentally. Okay, so this is the first example of how we can apply our AI technology for the ALD, inverse design of the dielectric material. So there are very interesting deep learning model, which is the diffusion model, and to improve the resolution of an image. If you have a very bad resolution image, by using this deep learning model, you can improve the resolution. The process mechanism is, if you have this clear image, you can intentionally make a noise and then more noise. Like it looks like you diffuse out one bitmap. And then you train this roof. And then if you have the not very clear image, you can improve that image by using this inverse loop. So this is the diffusion model. A year ago, Microsoft suggested really interesting approach. If you have the stable material, like if you have a rock solid material, you can diffuse out and then you can make the separate atoms and then train it and then put it back. You can fabricate it all possible crystal structure by using the element you choose. Like for example, if you choose silicon, oxygen, carbon, you just put into, you can have the all possible crystal structure of the silicon, oxygen, the carbon. So the impact of the diffusion model is because in the semiconductor process, there are very few number of elements they are now using. They only have like silicon, boron, phosphor, arsen, hafnium, zirconium. It's not too many. It's like around the 20. So we can choose those kind of elements and then we can fabricate it all possible crystal structure. So this is the one example. We choose the hafnium zirconium oxide and then we make this framework. And then we choose hafnium zirconium oxide to all possible crystal structure. And then the number of crystal structure is 20,000. So think about that. Can you make your 20,000 crystal structure by your hands, by your head? It's almost impossible. It's beyond our Homo sapiens capacity. And then we extract the physical property by using line graph neural network. It's a very well-known deep learning model. And then this is the result. All small dot, it's the one crystal structure, and then all trend looks like a very easily making great agreement with the experimental result. And then let's move on to the second example. I have 5 minutes more. And then the second approach is just quite different from the diffusion model. And then this is a fast screen of the precursor and an inhibitor. As I explained, ALD process is the very surface-sensitive deposition technique based on the chemical reaction. So in many cases, to decide, oh, this process can be applied on this surface or not, so we have to think about our precursor chemical can be absorbed on the specific surface or not. So conventionally, to see the deposition or not, or to see the blocking or not in the selective deposition, so we have to do experiments and then analysis, experimental analysis. We have to spend a lot of the time. But most of the paper talking about precursor absorption or not. And then they always say, oh, we have done that. Oh, no precursor absorption. And then yes, precursor absorption, no deposition, and yes, deposition. So their question is always going to be absorption or not, deposition or not. So we utilize machine learning, ASC, and we have a precursor and a substrate and a reactant. And we change that into the graph neural network number, and we make the pre-trained model. That means like if you have the A precursor, B reactant, and C substrate, so you can see a lot of the case, and then you train for those things. And then if I have the B precursor, hey, Boram, can you say this C precursor can be observed on the surface or not? I can say something based on my pre-training process. So most of the scientists cannot understand at this moment because most of the scientists really like the pattern. Like, for example, the most famous pattern in our science is F equal ma. Newton find this pattern. In humans' ability, so we can only find a very simple pattern, but by using the deep learning process, pre-training process, those computing power can find a very complicated pattern. So this is the secret. And then we can say absorption or not, deposition or not. So the way is, so we can put into the everything and then we can say right away the result of that, yes or not. So this is the initial result of that. And we can have the pretty high fraction. It's over 90%. And then this is the result. And then this is the real demonstration of that. So we have this paper, and that is independently published outside of my group. And we didn't include this result to the pre-training process. And then this paper taking care of PDMAS, which is the silicon precursor, and they use copper and silicon oxide substrate, reactant, ozone, and water using the different type of temperature. And then I said, I just put into all of the things, except one, they make the right answer. Absorption, yes. Experimental, yes. Absorption, no. Experimental, no. It's correct. But there is only one wrong answer. I think that because of this is the temperature was pretty much lower than the typical temperature. So we are trying to keep improving this process. Okay, this is summary. So we trying to apply the knowledge of AI to improve the real physical experiment, to improve the better semiconductor fabrication. Yeah, this is my research group. Thank you.